This is chapter 7, problem 21. This is the one with the plate. And there's a lot of explanation here to convince you that while the plate falls in the vertical, once it hits the ground, you don't need to worry about the vertical anymore because the plate's going to explode just parallel to the ground, so just in the x direction and the y direction. There is a change in momentum in the, call this the z, the vertical, the z direction, but you don't need to worry about that. So from a problem-solving standpoint, what's really going to happen for our before picture, it's just a plate sitting there, and the after picture, it's going to explode into these three pieces. One's going to go that way, and there's a much better picture in the book. One's going to go this way, and then there's that piece that's going to go straight down. So it's a plate, explodes into three different pieces, and in the before picture, it's not moving. So we can go ahead and apply right before and after the collision conservation momentum. And since we have velocities that are at angles here, as you can see in the book, we have some velocities and angles, we're going to go ahead and break everything into their components and then do conservation momentum for the x and y direction. Before I even really start in on the momentum stuff, I'm going to get the components. So this is 3 meters per second, and we have an angle here. This is 1.79 meters per second, and we're given an angle, we're given an angle here, and this one's just in the vertical at 3.07 meters per second. So I'll go ahead and write V. I'm going to call them, they already called them 1, 2, and 3, so I'll continue with that notation. So this is 1, 2, and 3. So we'll have V1 in the x direction and V1 in the y direction. We'll figure out what those two numbers are. We'll have V2 in the x direction, and we'll have V2 in the y direction. We could do this all with variables. If you want to see one like that, just let me know, and I can walk you through what it would look like with variables. I'm going to go ahead and get the numbers in here, since this is one of our our first assignment or one of our second or third 2D momentum problems. So we can get some numbers in here. It might help you guys out. And then V3 will just be in the y direction, and I'm going to call up and right positive. You can always assume that if I don't write it at this point in the course. But that'll be negative 3.07 meters per second. And I'm taking care of the sign right here. So when I do my momentum stuff, I've already addressed the signs with the components. So V1x will be 3 meters per second. That's measured from the vertical. You can do your SOHCAHTOA, but from the vertical, we're going to end up using sine for the x. So sine of 25 degrees, and then 3 meters per second cosine 25 degrees. Going up and to the left, so I'm going to make my x component negative. For V2, it's going to the right, so it'll be positive 1.79 meters per second times the cosine. We're measuring from the horizontal there, so cosine of 45, although it's 45 degrees, so it doesn't matter, and 1.79 meters per second sine of 45 degrees. So there we can represent all our components. And again, a little bit different from what I usually do in class. I'm taking care of the signs right now. So this x should be negative because it's going to the left. This x should be positive going to the right. Y components here and here are both going up, so positive, positive, and I've thrown the negative on here. So I've already addressed the signs right at the beginning of the problem. Now, conservation of momentum. Initial momentum in the x equals final momentum in the x. And in the before picture, there's 0. So 0 equals, I'm going to add up my x stuff. So my m1, I'll write it as variables here first just to make it clear. m1, v1x. But I'm going to make them all pluses because I've already taken care of the sign. If you're doing this just with variables, you'd throw a negative on right there. You'd throw a negative. So m1, v1x plus m2, v2x. And that doesn't have any x part of its momentum, so there's that. Initial momentum in the y equals final momentum in the y. All three of these have momentum in the y. Again, before it's 0, so if 0 equals m1 v1y plus m2 v2y plus my m3 times my v3. But again, if I hadn't already accounted for the sign right here, if I was doing this with variables, I'd go ahead and make this a negative and account for it there. Either place is fine when you're given all the numbers like this. So now we're set up, and I'm guessing we're probably solving for the masses. Yeah, find the masses of piece 1 and 2. So right here, I'll put checks by things I know. I know V1x, it's a number up there. I know V2x. So one equation, two unknowns, can't solve. Here, I'll put a check by what I know, again, the V's. And I know M3 and V3. So at this point, the physics is actually over. And it's two equations, two unknowns. I'm going to take it a couple steps further and then stop. For the algebra, on this one, feel fine to go ahead and grab your TI-89 if you have one and plug it in, or use a matrix C, or if you have a computer handy, Google for an equation solver and plug in the two equations to see if it spits out the right answer. It is an odd, so the answer should be in the back of the book. But I'm going to fill in the next step here. So 0 equals M1 times my V1x, which is negative 3 meters per second, sine of 25, plus my M2. Up here we've got an M2. We don't know that, so we're trying to find, times my, this is for the x direction, double check, make sure I got the right one. So x, V1x, V2x, so 1.79 meters per second cosine 45 degrees. So there's one of my equations with the numbers in that I'd be plugging into my equation editor or my matrix or however you want to solve it. Substitution will work as well if you don't have a calculator handy or a computer. So there's one of my equations. And then the other one here for the y direction, I'm going to write 0 equals M1, again, that's an unknown, times V1, that's supposed to be a y right there. So V1y is 3 meters per second cosine 25 degrees, plus M2, which we don't know, times V2y, which is 1.79 meters per second sine of 45 degrees, plus M3, and here's where I took care of my sine. I did it with the velocity, negative 3.07 meters per second. Oh, and I know M3. Apologize, I need to put that in there. So 1.3. So this is correctly labeled, but it has a value of 1.3 kilograms. So there's my second equation. If you'd like, you can turn this into a decimal, turn this into some, or some number, whatever it is, and expand that out. And let's go ahead and do that a little bit just to make this a little bit easier to plug into whatever. So 0, actually now, that's good enough. We'll stop there. And the answer is in the back of the book. So these should be your two equations. Solve for your two unknowns. Make sure you're in degree mode. And I didn't go over how I got these x and y components. If you need that, I have some other videos on that. Or just do SOHCAHTOA. So draw your right triangle right there. Draw your right triangle there. I'll give you a tip at this point in the course. Pretty familiar with how these work. I think if an angle is from the vertical, you end up using sine for the x and cosine from the y. If the angle is relative to the horizontal, you use x with cosine, and for the y, you use sine. So that's something you might want to remember. But if you ever think you got that mixed up, fall back to SOHCAHTOA. Don't start just basing stuff on memory. If you can't get from here to the equation, or excuse me, from here to the answer, again, it's algebra. Come in and I can check your algebra if you've shown enough steps, or just grab a computer real quick, use your internet connection, and look up for an equation solver. That's it for the plate problem.